Okay, we're in Giancoli Physics, AP Edition, 7th edition. We're working on problem number 18 today. Go ahead and jump in. That problem reads, water and then oil, which don't mix, are poured into a U-shaped tube, open at both ends. They come to equilibrium as shown in figure 1050, shown below. What is the density of the oil? That's what they're asking us for. They give us a hint there. It's very generous of them, really not necessary. But go ahead and wrap your brain around this problem, come up with a plan, pause the video while you do that, and come back and see what you come up with. Okay, again, general problem solving strategies. Draw a picture and identify quantities you have. With them already providing the illustration, it helps a lot. But we can still identify, we have a couple different linear dimensions here, different heights. So I have to maybe come up with some subscripts to distinguish those. They're asking us for the density of the oil. That's the question. What is the density of the oil? That's over here. Now we have a height here. I'm going to call that height oil to distinguish that height there. Now I've got water running through this entire tube here, but I'm going to select this piece here as the height of the water, and here's why. Because of Pascal's principle, they asked up here why the pressure is equal. You got points A and B here at the same height. All of this fluid here is the same fluid, which is water. So because Pascal's principle tells us the pressure is going to transmit through the fluid, I know the pressure at points A and B will be the same. Similarly, on the top of these columns, I've got atmospheric pressure. I got atmospheric pressure here. I also have atmospheric pressure here. So any difference between atmospheric and the point down here where they're the same, these pressures are the same. So therefore, the pressure added by this column and this column has to be the same. So that's kind of my starting point. Using our equations from our equation sheet, or if you're looking these up on the internet or out of your textbook, you should have fluids equations available that look something like this. I'm going to be using our generic pressure is rho GH, or density accelerated due to gravity times height. I'm going to apply that to these two sides. The pressure difference due to the oil has to equal the pressure difference due to the water over here. So that's the principle. So the pressure due to the column of oil has to equal the pressure due to the column of water. And again, I'm specifically talking about this piece of the water here. I make the substitution for my equation sheet. I have the density of the oil, acceleration due to gravity, which is the same for all, and then the height of the oil. That's going to have to equal the density of the water, again, acceleration due to gravity, which is the same for all, times the height of the water. As is often the case with many of these problems, my acceleration due to gravity is going to cancel here. The thing you're looking for is the density of the oil. I'm just going to rearrange this equation. Solve for the density of the oil, equaling the density of the water times the ratio of the height of the water column to the height of the oil. We have to do a little bit of segment addition math here to get this height of water, but that shouldn't be too difficult. The 27.2 centimeters of this entire height here, minus this difference of 8.62 centimeters there, should leave you with 18.58 centimeters. Just with a little segment addition from geometry. Now, maybe tempting to do some conversions here because these are not SI units. But notice I have a ratio here, so as long as they're in the same unit, they will cancel. And I can live with that. So no unit conversion required. So let's go ahead and put our numbers in. Again, if you don't have this number memorized by now, you can look it up on the internet or use table 10.1 out of the Giancoli text or a corresponding table in your textbook. 1,000 kilograms per cubic meter for water. My height of water in this case is the 18.58 centimeters. And the height of my oil is 27.2 centimeters. We're going to end up with a density that is lower than water, which should make sense because I'm having to use a greater column of oil to overcome the weight of the water to balance the pressure. So it should make sense that this oil density is going to be less. Also, it's floating on top of the water, so you have that as well. These numbers here, that's roughly 15 over 30. That's bigger than 15. That's less than 30. So it's going to be more than a half, so maybe 2/3-ish. So about 2/3, and this is 1,000. So call it 600 or 700. Should be in that ballpark. Go ahead and grab your calculator to see what you come up with. When you punch those numbers in, my calculator is telling me 683.1-ish. And again, that's kilograms per cubic meter. That is in the realm of what the mental math told us, so that's a reasonable number. Just to wrap this up, our significant figures, we're dealing with 3, looks like, here on everything. We're going to round this to 683 kilograms per cubic meter to be the density of the oil in the tube. That takes care of this problem. On to the next.